Right. Well, everyone, today we'll be going over divide and conquer. Just a quick show of hands, just to get, I guess, the experience level. How many of you came to like previous workshops and know what recursion is? Right, that's pretty good. And I guess just another show of hands. How many of you are in CS32? Because there will be a bit of overlap. Okay, all right. All right. So for today, we'll be doing our raffle for the workshop 2 weeks ago. And then we'll be going over recursion, doing a practice problem for that. And then we'll get into the, I guess, the big matter for this workshop, which is divide and conquer. Before that, we'll be going over time complexity, because one of the big things of divide and conquer is how it can speed up your algorithms, and we want to know by how much. And then we'll be going over two practice problems for that. Longest nice substring and shortest pair of points. Then we'll do a Kahoot, and if you want afterwards, you can stay for a contest. All right, so a quick review of recursion and DP. So recursion is just the process of a function calling itself. We usually do this when we have a function that solves a problem, and we can divide this problem into smaller subproblems. For example, when computing the factorial, you can split the factorial of n into n and the factorial of n minus 1, and then multiply them. And in this way, we can use recursive function calling to simplify our total life. For example, instead of having a for loop that multiplies through all integers from 1 to n, we can just have n times another function call, which makes our code a lot more readable. This is also used in depth first search. We don't need to know what it is for this workshop, but if you were here for week 2 or week 1 when we went over graph theory, depth first search is just a way to traverse through a graph, and we also use recursion for that. Dynamic programming is just recursion, but we have a small technique that improves the speed of it by a lot. And this occurs when the smaller subproblems that we're solving occur over and over again. When we have the subproblem occurring over and over again, we don't want to resolve it over and over again. Instead, if we can store the answer somewhere, it would make our problem solving a lot faster. So for example, when finding, let's say, the nth Fibonacci number, I guess a standard recursion code would look something like this. If we're looking for the 0th or 1st Fibonacci number, we just return 1. Or if not, we add the previous 2 and then return that. But do you see any issues with the solution? It gives you the right answer, but what might be one reason why we wouldn't like the solution? Well, one of the reasons is we would solve the same problem, like subproblem, over and over again. When we look at this diagram, for solving the 4th Fibonacci number, if you just go through the table, you see we solved the 2nd Fibonacci number 2 times, the 1st one 3 times, the 0th one 2 times. And for really big numbers, this will be like, you'll have to do like an exponential number of like solving problems, especially when we've already solved it once. We don't need to repeat solving this. So when we compute the same value, if we're computing the same value multiple times, one way we can fix this is just save the value of each problem in an array, so that anytime we come across a repeated subproblem, we can just pull the answer that we have rather than solving it again. So I guess what this would look like is you would create an array of size n. Basically, n is the number of problems you have. In our case, if we're computing the nth Fibonacci number, it's the n numbers below that. And then we save it in an array so we can call it when we need it. So for an improved code to find the nth Fibonacci number, up here we store all the previous Fibonacci numbers. And here, if we haven't solved for it before, we compute it, and if not, we just return our pre-computed value. Are there any questions with how DP works? All right, if not, we'll go into our first problem. So this problem is called anti-11. There is a link to the contest here. You can just, I guess, type it out, or there's a link to the slides in the bottom where you can find the contest. All right, and here is just a statement of the problem if you don't have it up. Basically, you have Danny Ocean. He only likes strings where there are no adjacent ones. Like he likes binary strings, which are sequences of zeros and ones, but he doesn't like it when any two ones are adjacent. So given a string of a certain length, you want to tell him how many binary strings there are where there are no ones that are adjacent with each other. And just take like 5-10 minutes for that. We'll go over in a bit just how you would start, and then you can work on it for a bit more, and we'll go over like a complete solution. How many of you would like a few more minutes on this? Yeah, all right. We'll take like 3 or 4 more minutes. You can keep working on it through the explanation. I'll just be going over an idea of how to start. All right. In the meantime, we can just go through a little bit of how we would start this. So for a lot of problems where you just don't know how to start, the best thing to do is just go over the really small cases. And in this case, when we want to see how many strings there are, the small string we can look at is really a string of length 1. So just, I guess, if we're doing a string of length 1, how many strings are there where no two ones are adjacent? Yeah. Yeah, it's 2. Like for 2 ones to not be adjacent, there needs to be 2 letters, or yeah, 2 numbers. And if there aren't any, then all our strings are valid. So the 2 strings that we have with length 1 are just 0 and 1, and both of them are fine. So the next biggest case we can deal with is two strings of length 2, and I have the 4 of them up here: 0, 0, 0, 1, 1, 0, and 1, 1. Of these 4, how many of these are fine? Well, if we just want the 2 ones to not be adjacent, then our string with the 2 ones, the 1, 1 at the end, that one's not valid, and all the other ones are. One thing I would like you guys to notice from this is that when we have a string that ends in 1, it doesn't make sense for us to put another 1 after it because we don't want any of the ones to be adjacent. If our string ends in 0, we can put whatever after it. It doesn't matter. But if we have a 1, it's not good for us to put another 1 afterwards. That being said, does anyone have an idea of how you could use recursion to solve this one? It could just be like what your sub questions are, what your functions are, how they relate to each other, just any ideas you might have. And in the meantime, we can just go through the next biggest case. Again, 1, 1 is unusable, but the other 3 are fine. And our next biggest case is when we have a string of length 3. So this 8 strings are listed above, and we have 3 strings that are not allowed: 0, 1, 1, 1, 1, 0, and 1, 1, 1. And here we have 5, but again, you see that for this string right here, the 2 corresponding are 0, 1, 0 and 0, 1, 1. And we can't add a 1 to a string that ends in a 1 because we don't want ones to be adjacent. Other than that, you can add whatever you want afterwards. Are there any questions so far about how we're just building up the cases? All right, then we'll just go on to a solution. So again, one thing we observed is that, if our string ends with a 0 and we know our string has been fine until that point, there are no adjacent ones, then you can add anything after a 0 or a 1, because in those last 2 characters, you won't disobey the rule of having 2 consecutive ones. But if your previous string ends in a 1, you can't add another 1 because we don't want the ones to be adjacent. So you can keep track of how many strings there are, valid strings that end in a 0, and how many valid strings end in a 1. And then using this, you can use recursion to get your final answer. So here's what a solution would look like. So if we're solving this problem for a string of length n, we're going to keep track of up here the number of valid strings that end in 0 and the number of valid strings that end in a 1. So for the number of valid strings that end in a 1, the previous n-1 characters, that string has to end in a 0 because you can't have two ones that are adjacent with each other. But for the strings that end in a 0, anything before it is fine. So we add the number of strings of length i-1 that end in 0 and the number of strings that end in 1 with length i-1. And once we go through this for loop, we're going to have for, I guess, all integers from 1 to n, the number of valid strings of length I that end in 0 or end in 1. And then in the end, we just return, I guess, the sum of those for n. Are there any questions about this? This is like the recursive part is hard to find. All right, if not, that's how you do anti-11, and we'll start to go into time complexity and divide and conquer. So just quick show of hands, how many of you are familiar with time complexity? You don't have to be too familiar. We'll go over like whatever you need to know here. Time complexity is, I guess, how just a way for us to measure how fast our algorithm is. And we use big O notation. What this means is it tells us the speed of our algorithm in the worst case. So we have a guarantee that it'll always be faster than that. And when we're calculating it, like the number of operations that happen, we don't care about constant factors or low order terms. Like if we do something n times and then n squared times, us doing it n times doesn't really matter because the n squared times or operations will grow that much faster. So for example, in the solution we just did, can anyone tell me what the time complexity of this would be? Again, the way we would do this is kind of look through how many operations happen in the solution and then remove any constant factors or low order terms. We just want a general idea of how fast our solution is in terms of n. All right, just to start, we can, I guess, look through how long each thing takes. Initializing arrays, this happens in constant time, and returning our answer only happens in constant time as well. So whatever our complexity is really just depends on this for loop, because that's where the most like computation happens. We run through the for loop n times, and inside we just do 2 operations. So in general, the number of operations is going to be around 2n. So the big O, or time complexity of this algorithm, is around O of n. Like, it'll approximately take n like operations to solve this problem. Does that make sense? All right. We just have that here. 2 operations to initialize the array. We go through the for loop, that's about 2n times, and then an operation at the end. And that, when you remove all the constant factors, remove all the low order terms, is O of n. All right. Knowing that, we'll go into divide and conquer, and then we can also study how fast our divide and conquer algorithms are. So divide and conquer is just recursion, but it happens in a slightly different way. The way we do divide and conquer problems is we split our, I guess, problem into 2 subproblems that are, I'd say, a roughly equal size. You solve these 2 subproblems, and then you combine your 2 answers to get a total answer. 2 examples of where we see this are in Mergesort. We also see this in tree operations. And in some cases, using divide and conquer can make your algorithm much faster, like in Mergesort, which we'll see in a bit. So I just want to quickly go over the strategies that you see in Mergesort and really most recursive problems. The big part is seeing how you can split your problem into smaller problems. Once you do that, you can assume that you can solve these subproblems accurately with your recursive algorithm. And the next big part is combining these two together. So you split your problem into subproblems, solve these, and then recombine your answers. With Mergesort, our problem is solving or sorting an array of n elements. And I guess in divide and conquer fashion, what we want to do is split this problem into subproblems. Can anyone tell me how you would split like this sorting array problem into two smaller problems? Yeah.
So the first half and the second half.
Yeah. So what we would do is we would split our array into two. What we get is these two smaller arrays, and we would sort these arrays. Do we have graphical? All right, so we split our array into two smaller arrays, and we sort the both of these. We are going to assume that we do it using our recursive algorithm. So you solve these two smaller problems using Mergesort. And then the next step will be merging these two arrays. The way we do this is, since we know our two arrays are sorted, and we start off by wanting the smallest element, we can just look at the smallest element in the two arrays. For example, look at the first element in the two arrays and take the smaller one. So in this case, the two smallest elements are 3 and 6. We know this because there is the smallest element in our two subarrays. So if we want to take the smallest element in our total array, we're just going to look at these two values and take the smaller one. In this case, 3 in the left subarray is the smaller one, and then we can move it into our bigger array. And then afterwards, we would just look at the next smallest element in the first array, in this case, 7. You would repeat through these steps to fill up your array. For example, here you have 7 and 6. The smaller one is 6, so we move 6 into our bigger array, and I guess move our pointer over, and we rinse and repeat. At this point, we've gone through all the elements in the right subarray, so all the elements left are in the left one. Can anyone tell me what we would do in this case? We've exhausted all the elements in our right array. The only thing left is in the left. So in this case, the two elements that we haven't yet inserted into our larger array are 12 and 7. These are the only elements that are left, and we know they're in sorted order. So we can just copy over all the other elements, which is 12 and 14. We can copy it over to the top, and we are done combining our answers. So how long does this kind of merge take? For each element in our top array, we just check the first elements in the bottom arrays and see which one is bigger. And this is O of 1, it's constant time. And we do this n times. So our total merge operation happens in O of n. So if you have an array of size n and you split it into two, you solve those two subproblems. The actual merging your answers back together takes roughly n operations. Its time complexity is O of n. Are there any questions about this part? If there's nothing else, we can just look through how our code actually runs through the whole Mergesort. So we start with this 8-element array. It'll split into two subproblems. Recursively, it'll split into more like subarrays and so on. When we get into arrays of like size 1, where there's only one element, we know this is automatically sorted. So we can just consider these sorted, and we merge back upwards. We go to the second layer with arrays of size 2, then size 4, then size 8. So we split our problem down into the simplest case. We solve that, and then we recombine our answers back up to get our final answer. So the time complexity of this. So the time complexity is important because some sorting algorithms on like in the worst case, can be like pretty slow, O of n squared. For example, one slow sorting algorithm is just every time you want to find the smallest element, just go through your entire array, keep a tracker for your smallest element, and then when you do that, move it to the front and repeat. That, for example, takes O of n squared, but this algorithm is much faster, as we'll see. So in the bottom layer, we have n subarrays, and merging these or getting the answer for this is each O of 1. So the total time complexity of this bottom layer is O of n. In this next layer, we have n over 2 subarrays, and merging or getting the answer for this is O of 2. Again, the merging is just O of whatever the length of the array is. So in this layer, your complexity is also O of n. Same with the next layer, and same with the last layer. So when we split this problem in this way into layers, the time complexity of each layer is O of n. So the last step we need to find the time complexity of our algorithm is just find the number of layers there are. Does anyone know how many layers there are when we split this problem recursively, splitting each array into 2? It's not going to be an overly complicated answer, and you don't need to worry about any constant factors if you find any either. It's just it's some function. So every time we go down a layer, we just split our array into 2 smaller subarrays. So the number of layers is just how many times we can do this. How many times we can divide n into 2 before getting to 1. And our function for this is the logarithm. So the number of layers is going to be log n. And that's just the number of times you can split n into 2 before getting 1. So we have log n layers, and each layer takes O of n time complexity. So our total time complexity is n log n. Are there any questions about this? In general, you don't need to, I guess, prove the time complexity of any of your answers, but you definitely want to know how to find the time complexity of your algorithm, just so you can know beforehand if your algorithm is fast enough. In a lot of competitive programming problems, they'll tell you the bounds on n. And for example, in this kind of problem, if n was like 10 to the 6th, log of n squared is too slow. That's 10 to the 12th operations. That's like 100 or 1,000 seconds. But n log n would be like in a fraction of a second. It would work more than fast enough. Are there any questions about this? All right, then our next part will be tree operations. Again, we went over trees in our first and second workshop, but it's basically you have n nodes and they're n-1 connections. And a lot of times in representing like a hierarchical structure, it'll just look like a tree where you have a node at the top, below it you'll have more nodes which are all connected, below it more nodes. It looks a lot like the diagram we have, and we have some notation. The top node is called the root node. Anything below it are the children of the node. So if we get a problem like you're given a tree with n nodes and you want to find I have a typo here, the maximum of all the nodes, we could do this using divide and conquer. So the way we would do this is split our tree into smaller trees. And we have this with our left subtree, which is in green, and we have our right subtree, which is in blue. We want to find the answers for this smaller tree. I have a typo here. It should be the max of the nodes, but can anyone tell me what the max value is in the left subtree in green? Yeah, 7. And the right one? Yeah. So the answers for our left and right subtrees are 7 and 14. So we've done 2 steps of our process. We split our answer into smaller problems. We found the answer for these problems. And now we want to combine them. So to combine our answers, you would just look at your left subtree, the right subtree. It'll tell you the maximum for all the other elements in your tree, except your root node. So really you just have your root node, which is a value 8. And then you have your other two maximums, which are 7 and 14. So from this, we can just take the maximum from these three and get a total maximum of 14. Are there any questions about this? The nice thing about this kind of problem or problem solving is it works for many more operations other than maximum. It could be find the product of all the nodes in a tree. It could be find the minimum, find the sum. If you're just looking for a node, you can search through a tree using divide and conquer. Divide and conquer helps us a lot in like graph problems and many other contexts. So we're going to go into our second problem, longest nice substring. This one's a bit different. It's going to be on a site called LeetCode. If you have been to an interview track workshop before, oftentimes they happen on LeetCode just because they're closer to the kind of problems you could see in interviews. But this problem is really nice at illustrating how divide and conquer works. So if you just want to follow this link, it'll get you to a platform where instead of reading all the input and output, you just solve the function itself, which should give the correct answer. And just a look at the problem statement. You have a string S, and it's nice if for every letter in the string, both the lower and capital of that letter exist. For example, here for lowercase a, lowercase b, lowercase a, and uppercase b, you get all 5 characters having the lower and uppercase. So that string is nice, but a string like this is not nice because there's a lowercase b but no capital B. So given a string, you want to find the longest substring that is nice. So for this problem, you would just split it up, find a smaller substring that is nice. And if there isn't, like in this string, you would just return the empty string. If you find multiple substrings that are nice and both equally long, you would just return the first. So take a few minutes to work on this, and then again, we'll go over a solution. Right. Does anyone want more time to do this? Right. If not, we'll start going over it. So first, one way we check if a substring is nice is just go through every letter and see if a lowercase and uppercase version of it exists. For example, if we were iterating through this string, when we see an uppercase A, we would check for a lowercase a. We would see it's there. So both these letters, the uppercase and lowercase a, are fine. The same for lowercase and uppercase e, and the same for lowercase and uppercase e. So one way we can just check if a substring is nice is just going through all the letters. And if it is, our entire string is nice. The string itself is the longest substring of a string, and we can just return that and be done. But if one of our letters is not allowable, and by allowable, I mean like the lowercase of it exists and the uppercase doesn't, or vice versa. If that exists, then the string is not nice. For example, for this string here, the lowercase z has no uppercase counterpart. So our string is not nice, and z cannot be part of our substring. The nice thing about this is that because z is not in the substring, our longest substring is either to the left or to the right. And if for divide and conquer, this helps us because it splits our problem into 2 subproblems. In this case, we have this left substring, YA, and we have the right substring, A, big A, and Y. And we know our longest nice substring has to be somewhere here. So this is 2 subproblems. We can solve these. For our left one, there's no lowercase y and there's no uppercase a. So both these letters are bad and we have no nice substring. And on the right, there's a lowercase and uppercase a. So all 3 of those letters are fine. And we have a nice substring of length 3. So to solve our original problem, we would just take the longest substring out of the both of these, which is A, big A, A. Are there any base cases? So in general, what we would do is iterate through all the letters. And if we find a bad letter, we would split our problem into 2. All the letters to the left and all the letters to the right. But at some point, we can't just split our problem into smaller cases. We just need to know the answer. So what are some base cases for which we already know the answer? Well, in this case, because we're always splitting up our problem, the base case would be any small string. So once our string is too small, we've reached a base case, we should know the answer. And if we have an empty string, there's obviously no substring for that, so we would return the empty string. And if our string is only one letter, we know that string cannot be nice. Can anyone tell me why? If, for example, our string is just a lowercase a, why is that string not nice? Well, in the case I just mentioned, there's a lowercase a, but no uppercase a. And if we had an uppercase a, there's no lowercase a. In general, for a string to be nice, you need both the lower and uppercase version, which means you need 2 letters. So if our string is less than 2 letters long, we know immediately it has no nice substring, and we can just return the empty string. So that would be our base case. We would just check if our string has a length less than 2, and if it does, we just return the empty string. So we have a kind of template for our solution. We have our base case where we just check the size of the string. Then we would go through our string and keep track of every letter that's acceptable. If all the letters are acceptable, then we can just return the given string. But if we find any letters that are unacceptable, we have our 2 subproblems and we just use recursion. So take a few minutes, try to fill in the template, and then we'll go over a complete solution. Would anyone like more time on this problem? All right, if not, we can just go over the solution. So our first step is just checking the base case. And as we said, any string that has a length less than 2, we know it has no nice substring. So at the top, we just check the size of S. If it's less than 2, we return the empty string, which indicates there's no nice substring. Now we go through the string and we store all the allowable or acceptable characters. The way we do this is we have 2 arrays, one for the lowercase letters and one for the uppercase letters. First, we initialize the 2 arrays, setting all the letters to false, because initially we have none of these letters. And when we go through the string, we just fill in this upper and lower array if we find the upper or lower letter. The way we do this, there's a small trick involved. So first we check if the letter we're currently at is uppercase. And if it is, we take that character and subtract it from capital A. The reason we do this is it gives us a nice way to get a number out of it to use as our index. What this expression basically tells us is how many positions after big A our letter is. So if the current letter S sub I is capital A, this returns 0. If it's capital C, it returns 25. So it just gives us a nice way to get the index of our array. And we do something similar for the lower array, where we subtract lowercase a instead of uppercase a. And once we have all of our acceptable and non-acceptable arrays or letters, we go through our string once more. Again, the way our solution worked is we go through our string. If every single letter is acceptable, then our entire string is nice and we return it. So if both the lower of I and upper of I are true, which means both characters exist, then we simply just continue because both the uppercase and lowercase letters exist. But if we don't, we have our 2 subproblems. S dot substring from O to I is all the letters to the left of our letter that's unacceptable, and S dot substring of I plus 1 are all the letters to the right. This just uses the built-in substring function, which is very useful in a lot of string problems. But that's just a way for us to get the 2 smaller strings that we're solving for. Once we do that, we just solve for the longest substring for these 2 strings, and then we return the one that's longest. Can anyone tell me what we do if both these strings have the same length? Well, in the code, we return the first string. And the reason we do this is because the problem wants us to find the earliest, longest substring. And if both of them have the same length, then the earlier one was in the first, it was in S1. So if the size of our first answer is greater than or equal to the second one, we return S1, the first one. If not, we return the second one. And again, at the end, if all the letters were fine, then we just return our total string and we are done. Are there any questions about this? All right, then we can go to our second problem, shortest pair of points. This one is going to be back on Caddis, so if you need it, here's the link again. And we have, oh, did you put the problem on the slide?
Oh, I don't think so. It's
All
pretty
right.
easy to explain.
All right.
Okay, so for this problem, essentially we're given n different points in a 2D coordinate plane, and then we want to find the pair of points that are closest together. So being closest together obviously means that their distance is the smallest. And so yeah, for this question, a few minutes to think about it and then see what you get. Okay, does anyone have any ideas for this question? Even slow ones are fine.
Really slow would be just checking every single pair and possible and find the smallest.
Yeah, exactly. So like he said, the simplest way we could do it is just to check every single point or every pair of points. And since there are n points, there would be n squared pairs of points. And so you'd have to spend like essentially n squared operations to find the shortest distance. So yeah, that would basically be taking every 2 points and then finding their distance and then take the minimum of that. Okay, so since the topic of the lecture is divide and conquer, obviously there's some divide and conquer solution here. And so the most intuitive thing that we want to do is we want to split the original n points into 2 different sets. So we'll do exactly that by taking some vertical line somewhere across the plane such that on the left of the line, there's going to be n over 2 points, and on the right of the line is going to be the other n over 2 points. And so now we'll just recursively solve for the closest pair in the left set and in the right set. So in this example, we have 8 points here. If we put the line as shown, then we have 4 points on the left, 4 points on the right. And so using divide and conquer, we first approach the 4 points on the left. So now we have the same question, but instead of 8 points, we only have 4 points. And so we can apply divide and conquer again. We split the 4 points into 2 points, or 2 sets of 2 points. And then now, does anyone know what the solution for the left set and the right set would be here? So we have 2 points on the left and 2 points on the right, and we solve for them separately. So does anyone know how to find the shortest distance here? Yeah.
You only have 2 points, so there's only one distance you need to check.
Yeah, exactly. So both sets only have 2 points, and so there's only 1 pair of points. So the minimum is just the distance between the 2 points. So cool. We know that for the left set, the closest pair is just that pair. And for the right set, the closest pair is also just that pair. So now we have the solution for these two. And let's go back to the original problem. So in the original problem, we had 8 points. And we're trying to find the closest distance between those 8 points. And let's say that we know the answer for the left 4 points, and we know the answer for the right 4 points. So for the left, it would be D1, and for the right, it would be D2. So does anyone know how we would obtain the closest pair in all 8 points, combining the answer for the left 4 points and the right 4 points? Since we're trying to find the minimum distance, does any like intuitive solution pop out here? Yeah.
Would it be that the next closest pair be between the two?
Would it like a point from the left?
Like in between the 2 closest pairs of each set? Or no?
Yeah, so that's a good idea, right? So if we have this is the closest pair in the left set, we have this is the closest pair in the right set. What if we just take like the smaller of the two, right? Is that what you're saying?
I don't know.
Yeah, so that's a really good idea. Well, what if we just take the minimum of these two pairs, right? So we have D1 here and we have D2 there. What if we just say that the closest pair is just the minimum of them? So it's the minimum of D1 and D2. So in this example, like you see D2 is slightly shorter than D1. And so we'll just say the answer is D2, right? Does that make sense, everyone? Okay, yeah. But there's one case we're missing, right? So we know D1 is the closest pair taking just the left points, and D2 is the closest pair taking just the right points. And if we take the minimum of those two, we get the answer like just keeping our points to like their separate sets. But what about the pairs of points that go from like the left set to the right set? Well, we haven't looked at the distances between those, and so we can't really say anything about the minimum of all pairs, if that makes sense. So does it make sense, everyone, why the answer isn't necessarily the minimum of D1 and D2? Like, for example, in this case, we have that this pair of points, they're just like visually closer, right? Okay, so we can adjust our answer here. It's not too difficult. Instead of taking the minimum among D1 and D2, we take the minimum of D1, D2, and every pair of points from the left half to the right half. So for example, we have this pair of points up there, we have this pair of points over there, and this pair down there. And if we take the minimum of all of those, then we know the minimum for every single pair. Does that make intuitive sense, everyone? Okay, cool. Now the question is, how do we find the minimum among the pairs between the left half and the right half? Well, does anyone know how many pairs we would have to look at in this case? Yeah. Yeah, so since there's n over 2 points on the left, n over 2 points on the right, the total number of pairs would be like n squared over 4, right? So again, that's another n squared solution, which is what we don't want. We want something faster. So does anyone see a way to reduce the number of pairs that we need to check? Okay, so let's say that D is the minimum of D1 and D2. So remember, D1 is the answer for the left half, D2 is the answer for the right half. And we said D is the minimum here. So in this case, D would just be D2. So let's consider all the points that lie within D of the vertical line here. So this would be essentially this like strip of gray. We're only going to consider points within that strip. And does anyone understand why we're reducing our search space like this? So would it be possible for the answer to be like some point outside of the strip, along with some other point on the right? Would that be a possible solution or no? Yeah, so it wouldn't be possible, right? Because if you have some point here that's not within like this strip of area, then the distance from all of these 3 points to some point on the right would be greater than D. Does that make sense? Why it's greater than D? So for example, if you took like this point and you took this pair with some pair on the right, then obviously the distance would be greater than D. And so we know that the pair wouldn't be the minimum. So we only have to consider points within the strip. So does this help with our time complexity, or is it still like pretty slow? Yeah.
That's gonna be faster, right? Because you're just considering less points.
Yeah, exactly. So again, we only consider the points within the strip and we throw all the other points out. So now instead of considering like four points on the left, 4 points on the right, we only have to consider one point on the left and 2 points on the right. So we've made a little bit of an improvement here. We've done some pruning, but it's still not as fast as we can make it. So there's some other optimizations you can do here. Okay, so let's say that we have just 1 point on the left. And we want to consider how many points we can pair it up with on the right. So for example, let's say we have all these white points on the right, and we have just this singular left point that's orange. So how many pairs do we need to consider on the right to this left point?
Why are all the white points evenly spaced?
Yeah, so the white points don't have to be evenly spaced, but we know that the distance d is the smallest distance so far. And so if there were points that were smaller than that distance, then d would be smaller. So they have to be at least within distance d of each other. And so since we want to find like the worst case, we're just going to put them all evenly spaced. Yeah, so I hope that explanation made sense. If it doesn't make sense, you don't have to imagine that they're evenly spaced. You can just imagine that they're anywhere. But yeah, so how many points on the right could we match with this orange point on the left here in order to get like a better answer? Yeah. Not exactly one. Why would it be one?
Like, because they're eating away. So, also notice. And then it's D. Or, like,
But you
it
could
should
also
be
have like you could also have this point, right? Like just imagine this point is
like,
exactly
about like, I don't know, 3 years ago, I feel like.
yeah. So okay, well, do we need to consider like this orange point and this point down here? Is that like a possible case or no?
For which white point?
Like this point all the way down here and this orange point.
No, it's at least 2D.
Yeah, so that distance would be at least 2D, right? So we know that we don't need to consider like the points on the bottom and on the top, but we only need to consider these points like in the middle section. And so does anyone know how many points could be in the middle section? A hint is that you can just count the number of blue points here. And if you count them, you'll get 6. So for every point on the left, you only need to consider 6 points on the right. At most, yeah. And so the reasoning is, well, the proof is by picture, I guess. You just look at the picture and then you see that there's only 6 points that are close enough to be less than D. So I hope that makes sense. And so, yeah, there's only 6 n pairs of points you need to consider from the left half to the right half. And so the total number of pairs we have that could be a contender for the minimum are those 6 n pairs and D1 and D2. So we take the minimum of all of those, that'll be 6n plus 2 pairs, which is just O of n. Okay, so just to recap, we split the problem into 2 halves. We find the answer for the left half and the right half, and we know that we can combine the 2 answers in O of n time. So I guess mathematically, what we can say is that if Tn is the time complexity for the original problem, we split into 2 problems, and then we combine it in O of n time. So that would be T of n is equal to 2 times T of n over 2 plus some constant, I think it's a constant, times n. And so does anyone know what this would evaluate to if you cancel out all the T of n's on the right side? So right now we have T of n and T of n over 2. But we want to just get T of n on the left side and like some simple expression on the right side, right? So anyone have any ideas on how to do this? So one thing that kind of makes sense here is if we substitute for T of n over 2 with 2 times T of n over 4 plus C of n over 2, then we can get T of n as an expression in terms of T of n over 4. And we see that T of n equals 4 times T of n over 4 plus 2 times Cn. And then we can just keep on repeating this. So we get T of n is equal to 8 times T of n over 8 plus 3 times Cn. And then if we keep on doing this all the way down, does anyone know what this would reduce to in the end? Yeah.
Well, the left part will just be n times T of 1.
Uh-huh. Yeah, so like you said, we notice that this is always like 8 times T of n over 8 or 4 times T of n over 4. So eventually this will become like n times T of n over n or just n times T of 1. So that's like the first term. What about this term on the right where it's like 3 times Cn or 2 times Cn? What will that become?
And log n.
Yeah, so we notice that like every time we divide n by 2, the number on the right goes up. So it went from 1 to 2 to 3. So if we just extrapolate here, we get that t of n equals n times t of 1 plus c n times log of n. And so in terms of like time complexity notation, this would just be O of n log n. So I hope that made sense. Okay, cool. That's it for the presentation. We have a feedback form up if you want to leave any feedback. Like if this presentation was too fast or too slow or too easy or whatever.
You get a raffle ticket for doing it.
Yeah, so please feel free to give us feedback. And then we also have our website up here for all our current events and stuff.